Okay, just wanted to go through the solution to this practice final exam question. Okay, so we have an open set in the real numbers, and we want to prove that it can be written as the disjoint union of open intervals. Of course, we allow that the interval could be like from minus infinity to b, or from a to infinity, or from negative infinity to infinity. Of course, that's like a trivial thing. So let me recall, well, really define what an open set of the real numbers is. Luckily, this should be familiar. Okay. What does it mean to be open? It means for all x and I, well, the definition I'll give, there exists epsilon greater than 0 such that x minus epsilon, the interval from x minus epsilon to x plus epsilon, is a subset of I. Okay. Okay. Now we need to know a couple facts about intervals. If I take two intervals that have a common point, then their union is also an interval. So let's phrase it like this. Let A and A, B, C, D be two intervals. Oh yeah, in case you don't know, let me tell you this notation. The interval from AB is just those real numbers x, such that x is greater than A and less than B. Okay, anyways. Okay, so this is just an aside. Okay, so let's take two intervals and assume x is in AB intersect CD, and then the union of the two intervals is an interval. And you can prove this if you want, but let's draw a picture. Here's the interval from A to B. Here's the interval from C to D. Here's x. There's a union of the two intervals. It's also an interval. Okay. We'll just take this as kind of given, but you can prove it if you want. I guess you could probably prove it by cases. It's just the kind of way that stands out to me. Okay. So now we want to prove claim for each x is in I, there exists ax, bx in R such that the interval from ax to bx is contained in I, but, oh yeah, also, sorry, x is in this interval, but ax and bx are not in I. Okay. proof. Let's prove this claim. Well, let's take AX to be the infimum of the set of all real numbers A, such that the interval from A to X is contained in I. And let Bx, that's going to be the supremum of those real numbers B, such that the interval from X to B is contained in I. Okay. Now we claim that so first let's claim that AX is not in I. Well, if it was in I, then we could find a little open interval around AX. So there exists epsilon greater than 0, such that AX minus epsilon, AX plus epsilon is contained in I. And now take this interval, well, first of all, AX plus epsilon is one of these elements here. So let's think about what should we do. But let's say that AX plus epsilon over 2 to X is contained in I, since AX plus epsilon over 2 is greater than AX, which is the inf, right? So since AX plus epsilon 2 over 2 is bigger than the inf, it kind of has to be like in this, has to satisfy this property. And also AX minus epsilon to AX plus epsilon is a subset of I, so their union is a subset of I. So that tells us that AX minus epsilon to X is a subset of I. But that means that AX minus epsilon is in all the set of A's, such that A to X is a subset of I. That's a contradiction. That basically that means that AX is not the inf of this set. Okay. And what is it a contradiction to? Well, we assume that AX is an element of I. So it must not be. AX is not an element of I. A similar argument tells you that Bx is not an element of I. Similar. Okay. Now we want to show that the interval from AX to Bx is a subset of I. So let Y be in the interval from AX to Bx. If Y is equal to X, then Y is an element of I. Well, because that is kind of given to us, we want to show that each element of I is contained in kind of like a maximal interval. Okay, I should know there's probably like a slicker way to do this, but that's okay. Okay. So we know that if y is equal to x and y is in I, well, the other cases are that y is less than x or y is greater than x. So if y is less than x, then y is in the interval from ax to x. And so it is so we can say that then y is greater than ax. So like having the distance between them, so we can say that so y is greater than ax plus epsilon for some epsilon greater than 0. We can take epsilon to be equal to what, like y minus ax divided by 2, for example. That would work. Okay, so therefore y is in the interval ax plus epsilon to x. Okay, but no, since ax plus epsilon now this interval has to be contained in I. Right. Okay. So y is an element of that, so y is in I. So now we've shown like anything from ax up to x is an element of I, and it is similar to show that anything from x up to bx is also an I. So if y is greater than x, then y is in I by a similar argument. Anyways, this shows that xbx is a subset of I. And now we can write I as the union over x in I of these intervals. Okay, and now the key is to show that this is really a disjoint union. Okay, now we claim, so let x and y be in I. We claim either ax equals ay and bx equals by, or these intersection is empty. Okay. And so suppose the intersection is not empty. Okay, Well, that means that the intersection of these two intervals is not empty. So that means that their union is also in an interval. Okay, what does that mean? Um, well, if we write this as the interval, let's write it as the interval alpha beta. This is an interval that is contained in I, because both of the intervals are contained in I. And x, since x is in ax bx, x is in this interval. Oops, it's the beta, not a b. And y is also in this interval. Okay. So that implies that, beta has to be less than or equal to bx, alpha has to be greater than or equal to ax. Okay. But alpha is actually the minimum of ax and ay. So alpha is also less than or equal to ax. So alpha equals ax. Similarly, beta equals bx. And for the exact same reasons, but with y instead of x, alpha equals ay and beta equals by. So in particular, alpha equals ax equals ay, beta equals bx equals by. So that tells us that any two distinct intervals are disjoint, and that means that we have written our open set as a union of disjoint intervals. Okay. The end. So thank you for watching. Any questions about that, please email me.